Okay, so we're going to talk about how to combine functions using division, composition, and decomposition. Now, we've already done combinations of functions in Module 1, where we learned how to add, subtract, and multiply functions. And so we're just adding to that. We're adding to that. We're going to cover division today, and then we're going to talk about composition and decomposition. So let's start with our notes. So we begin with, we know that the domain, so my first blank here, the domain of an arithmetic combination, adding, subtracting, multiplying, or dividing of two functions, in this case we're going to call them f and g, consists of all real numbers that are going to be common to the domain of f and to the domain of g. So what that means is this: when we say that they have to be common to the domains of f and g, we talked about this when we did combinations with addition, subtraction, and multiplication. When we talk about the domain, so if I'm looking at the domain of f plus g, or the domain of f minus g, or the domain of f times g, these will all be the same. I know that the domain of those combinations are the intersection of the domain of f with the domain of g. So that means that whatever my x values are for these combinations, x has to be this funny looking e, means an element of or within the domain of f. So x is going to be an element of the domain of f and the domain of g. So we'll always look at the domain of f, we'll look at the domain of g, and then we put them together to come up with the most restrictive, and that gives me that intersection, which is the domain of f and g. So that still holds true when we're talking about division. Okay, so in the case of continuing with our notes here, so when we're talking about division, in the case of the quotient, so we're looking at f of x divided by g of x, we're going to have one additional restriction. So we're still going to be looking at the domain of f's intersection with the domain of g, but with that additional restriction, we know that anytime we divide, we know that we can never divide by 0. Okay, we just know that breaks, all the crazy rules of mathematics, right? So g of x can never be 0. So that's my additional restriction, is that g of x, or whatever that denominator is, g of x cannot equal 0. Now, just as a quick little aside here, we're dividing by 0. So sometimes students get confused. So let's say I give you a function like g of x divided by h of x, then in this case, h of x could not equal 0. Okay, it's not that just g can't be 0. Once in a while I get a couple students that just think g across the board can't be 0. So just realize it's whatever is in the denominator cannot be 0, because we know we can't divide by 0. Okay, so moving on with our notes. Looking at the sum, the difference, the product, and the quotient of our functions. We know we've got, in this case, we're going to say we're going to let f and g be two functions, and they're each going to have domains of a and b respectively. So the domain of f will be whatever a is, the domain of g will be whatever b is. Then we know that when we're looking at the sum, the difference, the product, and the quotient of these two functions, they're going to be defined as follows. Now the first part here, sections, or numbers 1, 2, and 3, sum, difference, and product. This is just review. This is from Module 1. So f plus g of x we know is the same as f of x plus g of x. And the domain is going to be the intersection of f with the domain is going to be the intersection of a with b. So we've already said the domain of a is going to be what domain of f is, and that'll be the intersection with the domain of g. For the difference, f minus g of x is the same as f of x minus g of x. So the domain, again, will be the intersection of a and b, or the intersection of the domain of f with the domain of g. Okay, again, I'll review. F times g of x, so the product will be f of x times g of x, and then the domain, again, is whatever the domain of f's intersection is with the domain of g. And then the only thing new here, what we're learning new today, is about the quotient. And we know that the quotient is going to come with restrictions. So again, following the same logic here, we're going to have the f of x divided by g of x. And then the domain is that x is going to be an element of a's intersection with b, or we could write that as x is an element of the domain of f's intersection with the domain of g. And then this vertical line is read such that, okay, so that is read such that g of x does not equal 0. That's my new restriction that we've added today. So remember, g of x is just whatever the denominator is will not equal 0 because we can't divide by 0. Okay, so let's run through some examples because it's always a little less confusing that way. Okay, so in our example below, we're given a set of functions, and we're supposed to determine f plus g of x, f minus g of x, f times g of x, and f divided by g of x. And then we're going to determine the domain for each of those as well. So we always want to remember we're going to include the domain. And really, the addition, subtraction, multiplication, and division of these functions is not the hard part. It's the domain that tends to be a little tricky. And I think once you pick up on the pattern, I think you'll pick up on that pretty quickly. All right, so we'll do these one. So let's first look at f plus g of x. I'm just going to call that a. So f plus g of x, I know is equal to f of x plus g of x. Well, f of x, I'm told, is x squared plus 2x. G of x is x squared. So I just combine my like terms. So I have 2x squared plus 2x. And that is my answer. That is f plus g of x. Now, when I'm looking at the domain, I need to look at the domain of f, and then I need to consider the domain of g. And I know that the domain of the composed function, so the domain of f plus g, will be equal to the intersection of the domain of f with the domain of g. So let's look at the domain of f first. So I know that f is x squared plus 2x. That's a polynomial. That's a second degree polynomial, so it's a quadratic. And I know that polynomials have a domain of negative infinity to infinity because they're smooth, continuous curves, no jumps, no breaks. So the domain of f will be negative infinity to infinity. Now I'm going to move on and I'm going to look at the domain of g. Well, g is x squared. So again, a quadratic or a polynomial, so smooth continuous curve. So the domain of g will be negative infinity to infinity. In fact, you should be able to visualize both of these graphs look something like this, okay? F will be shaped just a little bit differently, but you have the general visualization of what the shape of the graph is, okay? All right, so now the domain of the combined function, which is 2x squared plus 2x, is the domain of f intersection with the domain of g. Well, I just look at the restrictions for f and look at the restrictions for g, and that gives me the combined domain. Well, there are no restrictions on f or g, so the answer is negative infinity to infinity. And that is the domain of f plus g. All right, so that's my first one. So let's move along. Let's do b, and we're told to find f minus g of x. So that, of course, is f of x minus g of x. This is all review. And that will be equal to x squared plus 2x minus g of x, which is x squared. So x squared minus x squared, those, of course, will cancel. And my answer is 2x. Okay. Again, when I look at the domain, I'm looking at the domain of f minus g. So I consider the domain of f, which we found above, the domain of g. And I know that the composition of those, or the intersection of those, is the domain of the composed function, and this, of course, is negative infinity to infinity. Okay, so C. Now we're going to look at f times g of x. So this is f of x times g of x. So f of x, again, is x squared plus 2x times g of x, which is x squared. We'll distribute. And so x squared times x squared becomes x to the fourth. 2x times x squared is 2x cubed. There's my combined function. And the domain of f times g, I know, is the intersection of the domain of f with the domain of g. Again, negative infinity to infinity. Okay. So I'll review. We haven't done anything new here. This should have been pretty straightforward for you. So this is all from Module 1. All right, so now let's look at what is new, which is the quotient rule. So we're going to look at f divided by g of x. So that will equal f of x divided by g of x. So again, f of x is x squared plus 2x. G of x is x squared. All right, now to simplify this, I can factor an x out of the numerator, so I'll have x times x plus 2 divided by x squared. I have an x in the numerator and an x in the denominator. I can cancel those. And then when I simplify, I will have x plus 2 divided by x. That is f divided by g of x. That's the combination. Now, when I'm looking at the domain, this one's a little bit different. So the domain of f divided by g is still the intersection of the domain of f with the domain of g. But remember, I have that additional restriction that g of x cannot equal 0. Well, the domain of f's intersection with the domain of g, I've already found 3 times above. I know that's negative infinity to infinity. And then g of x cannot equal 0. Back to the original g of x function, do not use the simplified combination. Okay, don't use just x here. That's not what I want. And matter of fact, I'm going to erase it so that you don't get confused. Okay, so g of x cannot equal 0. Well, g of x was x squared. So that means x squared cannot equal 0. I'm going to solve for x, so take the square root of both sides. X cannot equal 0. So when I'm looking at the domain of f divided by g, I have to put all of this together. I have to consider both of these. I know that the intersection is negative infinity to infinity, but I also know that x cannot equal 0. So the domain, the domain of f divided by g is going to be equal to negative infinity to 0 union 0 to infinity. And so if you want to see that on a number line, I know that the intersection of the domain of f with the domain of g is negative infinity to infinity, but x cannot equal 0, so it can be anything else. So negative infinity to 0 union 0 to infinity is your final answer for the domain of f divided by g. Now, let's look at another one. It's not on your paper, but we're going to just add this because I just really want to drive this point home. Let's look, what if I had asked you to find g divided by f of x, okay? Well, that would be g of x divided by f of x. G of x is x squared divided by f of x, which is x squared plus 2x. Again, we're going to simplify. So this is x squared divided by x times x plus 2. I can cancel an x in the numerator and an x in the denominator, and I'll be left with x divided by x plus 2. So now I want to know what's the domain of g divided by f, okay? Well, that'll be the intersection of the domain of f with the domain of g, which I know is negative infinity to infinity. And then now, again, I've got the restriction that whatever's in the denominator can't be 0. In this case, in the denominator, I had f of x. So what that means is that x squared plus 2x cannot equal 0. I need to solve for the x values that would make that true. So I factor out an x, so x times x plus 2 will not equal 0, which means we'll set each of these factors equal to 0. X will not equal 0. X plus 2 cannot equal 0. Subtract 2 from both sides, and so x cannot equal negative 2. So 2 additional restrictions here. So if I was using a number line for this one, I'm actually going to erase this other one just to get it out of my way. So now using a number line, the intersection of the domain of f with the domain of g we said is negative infinity to infinity. But then I have these 2 additional restrictions that x can't be 0 and x cannot be negative 2. So 0, negative 2. But it can be anything else. So the domain of g divided by f, I'm going to run out of room here. Let me do it this way. Okay, so the domain of g divided by f is going to be negative infinity to negative 2, union negative 2 to 0, union 0 to infinity. And that is my final domain. Okay, so make sure that you understand that when we're looking at that additional requirement for division, that because we can't divide by 0, whatever the function is that's in the denominator, we know that that cannot equal 0, and then we're going to solve that to find the x values that would cause that to happen. Okay, so if we were in class together, I would have you do number 2 on your own. And again, I want you to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x, and then determine the domain of each of these. So I want you to pause the video. I want you to go do that work, find those 4 functions, find the domains that go with them, and then come back here and check your work. Okay, so hopefully you've worked these, and let's come back and we'll run through these quick and check your answers. So for f plus g of x, you should have 7x plus the square root of x, and you can't simplify that. That's as simplified as it gets. There's no like terms. So let's do addition, subtraction, and multiplication and find the combinations first, and then we'll talk about the domains. So for f minus g of x, you should have 7x minus the square root of x, and the f times g of x, you'll have 7x times the square root of x. Those are your combinations. Now, the domain for all of these, addition, subtraction, and multiplication, the same. So once you find the domain for one, you've found it for all 3. So first thing we need to consider is the domain of f. Well, f is 7x. So 7x is just a line, and so we know the domain of a line is negative infinity to infinity. For g of x is equal to square root of x. That's a square root. Okay, so we know what that looks like. Let's see if I was going to sketch a graph of it, something like this. Okay, and so the domain is that we know that whatever's under the radical, in this case x, has to be greater than or equal to 0. So when we're solving for the domain, x must be greater than or equal to 0. So the domain is 0 to infinity. Make sure you have a bracket there because 0 is included. So now when I'm finding the domain of f plus g, f minus g, and f times g, I'm going to take the intersection of the 2 domains. So domain negative infinity to infinity. Domain of g was that x had to be greater than or equal to 0. So put the restrictions together and you get a combined domain of 0 to infinity. Again, make sure you have a bracket with the 0. So that's addition, subtraction, multiplication. Again, all review from module 1. That should have been pretty easy for you. Now let's talk through what's new. So next we're going to find f divided by g of x. So that'll give me 7x divided by the square root of x. Now, if you remember back in middle and high school, you can't leave a radical in the denominator. We need to rationalize that. So to rationalize, we're going to multiply by the square root of x divided by the square root of x. And then my final answer will be 7x times the square root of x divided by x. And so that is the combination of f of x divided by g of x. Now, for the domain, I'm going to first look at the domain of f's intersection with g, which is what I found above. And so that's 0 to infinity. These are the same. Okay, nothing new here. But now I need to add that additional restriction, that new restriction, which is that whatever is in the denominator, in this case g of x, can't equal 0. So that means the square root of x can't equal 0. Square both sides, and you'll find that x cannot be equal to 0. So I'm going to put that together to come up with my combined domain. So for the domain of f's intersection with g, I know that I'm going to have, let's see, 0 to infinity is the domain. But then that additional restriction tells me that x cannot equal 0. So then when I put that together, I get a domain for the combination of 0 to infinity. Make sure that you have a parenthesis because x can't include 0. And so we want to make sure that the 0 is not included. Okay, so hopefully you did well on that. Okay, so let's do another example. We're going to do one that's just a little more complicated. So this time I've been given the function f of x is equal to the square root of 9 minus x, and g of x equals the square root of x minus 4. And we're going to determine the quotient, and then we are going to find the domain for each one of these. So first, we're going to do f divided g of x. So f divided by g of x is going to be equal to the square root of 9 minus x divided by g of x, which is the square root of x minus 4. Again, I'm not going to leave a radical. I need to rationalize. So I'm going to multiply by the square root of x minus 4 divided by the square root of x minus 4. And then this will equal the square root of 9 minus x times the square root of x minus 4 divided by the square root of x minus 4 times the square root of x minus 4 is x minus 4. Okay, my combined function of f of x divided by g of x. Now I'm ready to work on the domain. Well, again, we always look at the domain of f first, and then we look at the domain of g. So for the domain of f of x is equal to square root of 9 minus x. Okay, so when I consider the domain, I know that whatever's under the radical has to be greater than or equal to 0, because I can't take the square root of a negative number and get a real result. I'll get an imaginary number. That's coming later in the semester. So whatever that is that's under the radical, in this case 9 minus x, has to be greater than or equal to 0. So I'm going to solve for x. So I'll subtract 9 from both sides. So I have negative x is greater than or equal to negative 9. Now be careful here. Remember, you're going to divide both sides by negative 1. And when we divide by a negative, it flips the inequality. So x will be less than or equal to 9. So there's my answer for the domain of f. Now I want to look at the domain of g. Domain of g is, let's see, g is the square root of x minus 4. So for the domain of g, whatever's under the radical, again, this is x minus 4, has to be greater than or equal to 0, which means x is greater than or equal to 4. So now, when I'm considering the domain of the combination, so the domain of f divided by g, I have to put all of this together. Okay, so I know so far that x has to be less than or equal to 9. Let's go ahead and create a number line. Okay, x has to be less than or equal to 9. We'll use a closed circle since it's less than or equal to. Greater than or equal to 4. Okay. But remember, we have one additional restriction here. Okay, so far I've found the domain of f's intersection with g. I also need to know, well, let's go ahead and do that. Let's see. The intersection of the domain of f with the domain of g then is 4 to 9. Okay, and then remember that additional requirement is that whatever is in the denominator, in this case g of x, cannot equal 0. So that means the square root of x minus 4 does not equal 0. We're going to solve for x, so we'll square both sides. X minus 4 will not equal 0, and so x does not equal 4. So that's my additional restriction. So far I know that it has to be greater than or equal to 4, less than or equal to, but can't equal 4. Okay, so when you put all that together on your number line, instead of this being a closed circle here at 4, I'm actually going to have an open circle. So let's erase that. And so we'll have an open circle at 4 all the way to and including 9. Okay, so that means that my domain for f divided by g is going to equal 4 to 9. 4 is with a parentheses because it's not included, 9 with a bracket because it is included. So that's my final answer. So finding the actual combination, which was the square root of 9 minus x times the square root of x minus 4 divided by x minus 4, that's the easy part. Finding the domain is a little more complicated. So now I want you to do the second one by yourself. I want you to do g divided by f of x here and find the domain. So find the combined function and then find the domain, come back and check your work. So pause the video. Okay, so you should have the quotient g of x divided by f of x is equal to the square root of x minus 4 times the square root of 9 minus x, all divided by 9 minus x. Make sure you rationalize the denominator. And then the domain of G is x must be greater than or equal to 4. The domain of f is that x is less than or equal to 9. And then remember that additional restriction is that the denominator, which in this case was f of x, cannot equal 0. So that means the square root of 9 minus x can't equal 0. Square both sides. You'll find that x does not equal 9. Put all of that information together. It's always nice, it's always nice to use a number line to do that. I know that x is greater than or equal to 4, less than or equal to 9, but x also cannot be 9, so that means we're going to use an open circle. And so my domain for G divided by f will be 4 to 9. Be very careful with your parentheses with the 9 and your bracket with the 4. Now, I'd like for you also to flip over to the lab manual and do one additional problem. You need to do lab manual, page 64, problem number 5. And the key is posted on Blackboard for you. So take a look at the key after you finish that. Make sure you got it right. Then come back to the video and we will talk about composition and decomposition. We've finished combinations of functions. We've talked about addition, subtraction, multiplication, and division. So those are combinations of functions. Now we're going to talk about composition of functions. So they're different ideas. So try to keep the different, keep your vocabulary straight. Combinations, when you combine two functions by adding them, subtracting, multiplying, or dividing. Composing two functions is when one function is composed with another. And so we're going to get into that now. On this page of our notes. So beginning at the beginning of our notes, another way of combining two functions is to form the composition, that's your first blank, of one with the other. So for instance, let's say that f of x is equal to x squared and g of x equals x plus 1. So f of x, x squared, that's a quadratic. G of x is equal to x plus 1. That's, of course, a line. And if we are looking at the composition of f with g, then that would be written as f composed with g of x. So when we talk about a composition, we replace, similar to how if we were doing, let's do a little aside here. Let's say I had a function f of x equals x plus 4. Okay, it's just a linear function. And I know that whatever I put in for x, then I'll use that to find my output. So let's say x is 2. So f of 2 would equal 2 plus 4, which of course equals 6. So all I've done here is I've replaced the x value, what if, in this case with 2, and then everywhere in the function there was an x, I replaced it with 2. Okay, easy enough. So when we talk about the composition of functions, it's the exact same idea. But now, instead of replacing x with a value, you're going to replace x with another function. And so in this case, you would replace x with whatever the function g of x is. Let me get my highlighter here. Okay, so instead of putting a number in, we're going to put in whatever g of x. So f of g of x would equal f of x plus 1 because x plus 1 is g of x. And so then in my function where f of x is equal to x squared, okay, then everywhere there's an x in my function, I would replace it with x plus 1. And so then it becomes x plus 1 squared. And so we read that as f composed with g. That's how you read that. And so, or f composed with g of x. So the composition, back to our notes here, the composition of the function f with the function g is f composed with g of x, and that is equal to f of g of x. So the domain of f composed with g, so this is read f composed with g, is the set of all x's that are in the domain of g such that g of x is also in the domain of f. So that's really wordy. What we're trying to say here is when we're looking for the domain of the composition, we're looking at all of the x values that will be in the domain of g, okay, such that g of x, where g of x is the output values, so g of x would be my outputs, are in the domain of the original function f. So the domain of f composed with g, notice that little circle is red composed with. So f composed with g is equal to the domain of g intersection with the domain of f composed with g. Okay, so what we're going to do is we're going to look at the domain of g, so the domain of the inside, and then we'll intersect that or find that where that comes together with the domain of the new function f composed with g. Okay, so let's walk through one of these, and I think it'll be more clear. All right, so for my first example here, it says, let f of x equal x squared and g of x equal x minus 3. And then we're supposed to determine f composed with g of 5. Okay, and so that's the same as f of g of 5. Okay, so the first thing I want to do is I'm going to find g of 5. I always start from the inside and I work my way out. So find g of 5. Well, I know that g of x is equal to x minus 3. Okay, so g of 5 would equal 5 minus 3, which of course equals 2. Okay, so g of 5 equals 2. So that is going to be replaced in this function. So I'm going to now evaluate f of g of 5. Well, g of 5 is 2, so f of 2, and that will equal 2 squared, because I know that f of x equals x squared. Okay, so that means f of 2 equals 4. So that's my final answer. So I have f composed with g of 5, and my final answer then is 4. Okay, so let's try the next one for b. G composed with f of negative 7. So first thing I need to do is I'm going to evaluate this. Well, let's see, let's rewrite it this way. This will be the same as, whoops, not g. F, nope, sorry, g of f of negative 7. Okay, so first thing I'm going to do is I'm going to evaluate f of negative 7 off to the side, and that will equal negative 7 squared. Negative 7 times negative 7 is positive 49. So positive 49 is f of negative 7. So we'll replace that. So substitute in place of f of negative 7, we'll use 49. So g of 49 then equals 49 minus 3, or 46. So that is my final answer. So g composed with f of negative 7 is equal to 46. So for parts A and B, we found f composed with g of a value and g composed with f of a value. So those are points on the graph, okay? And so we don't have to worry about the domain. We've found the output value. For part C and for part D and E, we're going to be looking at finding the composition of the two functions, so f composed with g of x in part C, and then the domain. So we want to know what the domain is then for the composition of the function. So part C, we're going to find f composed with g of x. So that is the same as f of g of x. And then similar to how, say, we were evaluating maybe, like we said, f of 4 for a function, then everywhere if we had like x plus 2, and I would replace all of the x's with a 4. Well, now for f composed with g of x, everywhere there's an x, instead of replacing with a value, I'm going to replace with that g of x value. Okay, so f of g of x is going to be f, which is x squared. So in place of x, I'll replace with the g of x value, which is x minus 3 squared. Okay, and then we can further simplify this if we want to, and it'll be x minus 3 times x minus 3, which of course we can FOIL, and that's x squared minus 6x plus 9. And that is f composed with g of x, which of course is a quadratic. Okay, now for the domain for compositions is sort of a three-step process. First, we look at the domain of the inside. So the domain of the inside function is the first that we need to consider. So in this case, our inside function is g of x. okay? And so when I talk about the domain of the inside, I'm talking about what's the domain of g of x? Well, g of x is x minus 3, which is a line. So the domain of g of x is negative infinity to infinity. Okay, step 2, we're going to look at the domain of the composition. So of the newly composed function, the domain of the composition. So we'll be looking at the domain of f composed with g. Well, f composed with g, of course, is our function x squared minus 6x plus 9, which is a polynomial. And so the domain of f composed with g is also negative infinity to infinity. And then my final answer, I have to consider both of these. So my final answer is going to be the intersection of the domain of g with the domain of f composed with g. So since they're both negative infinity to infinity, then that will be negative infinity to infinity. There's no additional restrictions here. And so that's the domain of the composition. Okay, so part D, scroll up a little bit here. Now we're looking at g composed with f of x, and we want to know what its domain is. So we're going to be looking at g composed with f of x is going to be g of f of x. Okay, and so now we'll start with the g of x function. If you look back up, g of x is equal to x minus 3, and f of x equals x squared. Well, everywhere that there is a x in the g of x function, we're going to replace it with whatever f of x functions is. So since f of x is x squared, this will be x squared minus 3. And all I've done is I've taken the f of x function, which was x squared, and I've replaced in g of x, in place of x, I put x squared for x. Okay, and then of course simplified, that is simplified, so there's nothing else I can do. So my final answer then is x squared minus 3. Now again, when I'm looking at the domain, I'm going to start with the domain of the inside. So the domain of the inside is f. So since f of x squared, that's a quadratic, which of course the domain is negative infinity to infinity. And then I'm going to look at the domain of the composed function. So the domain of g composed with f, which is the new function that we just found, which was x squared minus 3. And the domain for that will be negative infinity to infinity. And then, of course, the answer is the intersection of the two. So it's the domain of f's intersection with the domain of g composed with f, which is negative infinity to infinity. And that's my final answer. So what I'd like you to do now is I'd like you to take a look at E. E is f composed with f of x. See what you can do with this. Pause the video, take a shot at this, see if you can find the composed function, and then see if you can find the domain. Come back and check your work. Okay, so let's see how you did. So f composed with f of x is equal to f of x. So I take my inside function, which is f of x, and of course f of x is x squared. So everywhere there's an x within the f function, I'm going to replace it with x squared. So I'll get x squared squared, which of course then equals x to the 4th. So that's my composed function. And then when looking at the domain, we look at the domain of the inside, which is f. So the domain of f is negative infinity to infinity. Then we look at the domain of the newly composed function, which is f composed with f, which is x to the 4th, which again is a polynomial, and the domain of a polynomial is negative infinity to infinity. And then finally, our answer is the domain of f's intersection with the domain of f composed with f, and that answer is negative infinity to infinity. So far, all of these have been negative infinity to infinity, which isn't very interesting, but we'll get to some in just a bit where either the domain of the inside has an additional restriction, or the domain of the composed function has an additional restriction. And then when we find the intersection of those two domains, then that'll give us a different domain other than just, negative infinity to infinity.
If we were in class together, I would ask you to work this first example where f of x is equal to 4x minus 2 and g of x equals 3 minus 2x squared, and evaluate each of the expressions below. So I'd like you to pause the video here, work A, B, C, and D, and then come back and check your work. Okay, so hopefully you've completed A, B, C, and D, and Also, you should find the domain for each of these. So if you didn't do that, pause quick, do that, and then come back, and we'll talk through each one of these. Okay, so for the first one, we're looking at f composed with g of x. So that's f of g of x. So that means that everywhere within the f function that I have an x value, I'm going to substitute g of x. So I know g of x is 3 minus 2x squared. Okay, so that's going to go inside my function for f of x. So I'll have 4 times, and then I had x, so I'll replace the x with the g function, 3 minus 2x squared, and then minus 2. Make sure you distribute your 4 throughout the binomial, so 4 times 3 is 12, 4 times negative 2x squared, of course, is negative 8x squared minus 2. Simplify, combining your like terms, and your final answer is negative 8x squared plus 10. Now we need to look at the domain. Well, remember, when we look at compositions, we look at the domain of the inside, so in this case, that's g, so the domain of g. Well, g is 3 minus 2x squared, which is a polynomial. Polynomial domains are always negative infinity to infinity. Then we look at the domain of the composition, so the new function. And so my new function, of course, is negative 8x squared plus 10. And that also is a polynomial, so the domain, again, is going to be negative infinity to infinity. And then my final answer for the domain of the composition is the intersection of the domain of the inside with the domain of the new function. And so that, of course, will be negative infinity to infinity. For part B, we're looking at the composition of g composed with f of x. So now I'll start with my g function, and then everywhere there's an x value, I'm going to substitute with f of x. So f of x will replace all of the x's. So 3 minus 2x squared, and in place of x, I'm going to replace with the f of x function, which is 4x minus 2. So 4x minus 2 squared, you're going to have to FOIL that. So 4x minus 2 times 4x minus 2. Make sure you use brackets with that, and then when you're done, you multiply the whole thing by negative 2. So after you combine like terms, your final answer is negative 32x squared plus 32x minus 5. That's g composed with f of x. Then for the domain, we look at the domain of the inside, which we already found over actually, I guess we didn't. I should have written that out. So the domain of the inside, the domain of f, well, f is 4x minus 2. That's just a line. So the domain of a line is negative infinity to infinity. And then the domain of the newly composed function, so that'd be the domain of g composed with f. Well, that's a polynomial, so negative infinity to infinity. And then finally, your final answer is the intersection of those two domains, which is negative infinity to infinity. So that's B. For C, we're going to find f composed with f of x. So we'll start with the f of x function. Everywhere there's an x value, we'll replace that x with the f of x function. So 4 times 4x minus 2 minus 2. So again, f of x is equal to 4x minus 2, my highlighter here, 4x minus 2, and so within the f of x function, I've replaced the x with 4x minus 2. Distribute the 4, combine your like terms, and your final answer is 16x minus 10. Then we're going to find the domain. Again, the domain of the inside, domain of f is negative infinity to infinity. Then the domain of the newly composed function, well, the newly composed function is 16x minus 10, which also is a line, so negative infinity to infinity. And then the final answer is the intersection of those two, so the domain of f's intersection with the domain of f composed with f is negative infinity to infinity. All right, so part D was a little bit tricky. Hopefully you caught it. A, B, and C are all compositions, okay? Part D is actually multiplication. So part D is what we did in Module 1. So this is multiplication. This is not a composition. So I'm looking at f of 2 times g of 2. So I just take the f function, replace the x values with 2, take the g function, replace the x values with 2, so here 2 and 2. Do a little bit of algebra, and then your final answer should be negative 30. Now for this one, we don't have to worry about domain because this is the point on the graph. I know that when I'm looking at f of 2 times g of 2, I produce a new graph, and so this gives me a point on the graph, and that point is 2, negative 30. So I don't have to worry about a domain here. This is just a point. Okay, so that's my first example. All right, moving down to the bottom of the page, we're given f of x equals x squared plus 7, and g of x equals the square root of x minus 2, and then we're going to evaluate each of these expressions. So you shouldn't have any trouble evaluating the expressions. I want you to do this on your own again, and then you're going to find the domain for each one of these. Be careful with the domain. Make sure you apply what you know about domain, especially for that g of x function. This is probably the first one we're actually going to have something a little more interesting going on. So pause here, work on A and B, and then come back and see how you did. So for part A, we're finding the composition of f composed with g of x. So f of g of x, so just everywhere within the f of x function that there's an x value, we're going to replace that x value with g. And of course, g is the square root of x minus 2. So you get the square root of x minus 2 squared plus 7 gives you x minus 2 plus 7 combined like terms, and your answer is x plus 5. And then for the domain, we're going to look at the domain of g, so the domain of the inside. Well, for the domain of g, since g is the square root of x minus 2, we know that whatever's under the radical has to be positive. I can only take the square root of a positive value, so, or 0. And so whatever's under the radical, in this case x minus 2, has to be greater than or equal to 0. So this has to be greater than or equal to 0, which means x must be greater than or equal to 2. And then we look at the domain of the composition. Well, the composition is x plus 5, which is a line. So the domain there is negative infinity to infinity. Put that together. Remember, your answer is the intersection of the domain of g with the domain of the newly composed function, in this case f of g. And so your answer is bracket 2 to infinity. All right, for part B, we're looking at f composed with f of x. So again, anywhere in the within the f of x function that we have an x value, we're going to replace it this time with the f of x function again. So we'll have x squared plus 7 squared plus 7. So x squared plus 7 squared is going to be x squared plus 7 times x squared plus 7. FOIL that out. You'll get x to the 4th plus 14x squared plus 49, and then of course plus 7. Combine your like terms, and you have x to the 4th plus 4x squared, 14x squared plus 56 is your final answer for your composition. Look at the domain. The domain, we're going to look at the domain of the inside, which in this case is the domain of f, negative infinity to infinity, since it's a polynomial. Then the domain of, sorry, I've got a mistake here. I'll fix this. Then we're going to look at the domain of the newly composed function, which is the domain of f composed with f. That's negative infinity to infinity. And then finally, your final answer is the intersection of those two, which is negative infinity to infinity. So far, we've worked algebraically to find compositions of functions where we take one function and we substitute it into the other, and then algebraically we solve for the answer. We can also do it graphically. And so we've got a graph here on the right. You can see that the graph of we've got a graph of a polynomial. That one is g of x. Let's see if we can differentiate these to make life a little easier. So g of x is this polynomial curve. And then we have the graph of an absolute value. And so that is f of x. And so we'll make that one red. Okay, so we've got a polynomial and we have an absolute value graph. And then for parts A, B, C, and D, we're asked to determine g composed with f of 1, g of f of 0, f composed with g of 0, and g composed with g of negative 1. And to do that, what we're going to do is we're going to use the points on the graph. Okay, so let's work through one of these and see how this works. So for the first one, g composed with f of 1. Well, that's the same as g of f of 1. So what that means is we need to find what f of 1 is. So off to the side, I'm going to find f of 1. So f of 1, so remember f is the red graph. So find f of 1. F of 1 is this point here. 1, negative 1. So f of 1 is negative 1. So that's the substitution I'm going to make here for f of 1. So now I'm looking at g of -1. So g is the yellow graph, so g of -1 is the point 1, 3. And so I can see that that equals 3. So my final answer is 3. So g composed with f of 1 is 3. Okay, now let's do b. G of f of 0. So again, off to the side, I need to figure out what's f of 0. So we'll say, okay, f of 0, I can pull that from the graph. It's the red graph. F of 0 is the point 0, so 0, 0. Okay, I can substitute that in, and so now I'm looking for g of 0. Well, on the yellow graph, g of 0 is, it looks like 5 to me, and so your final answer is 5. Okay, so I would like for you to try C and D, and then come back and check your work, and we'll see how you did.
Okay, so for C, you'll find that G of 0 is equal to 5. So then you'll evaluate F of 5, and that's equal to 1. D, you'll first determine that G of -1 equals 3, which means you're going to evaluate G of 3, and that also equals 1. Okay, so part E is a little bit different. We're supposed to determine the X value, which makes G divided by F of X undefined. Okay, so I want you to pause here. I want you to think through this for a minute or two. See if you can determine which X value would make G divided by F of X undefined. Okay, so hopefully you really did think through this for a second first. It'll help you so much more when I ask you to pause and do things on your own if you really do, as opposed to if you just continue with the video and let me tell you the answer. Struggling a bit or really pausing to think about some things, you're going to learn a lot more that way. It's going to stick with you a lot better that way. So when I ask you to do that, please really do. It's really going to benefit you down the road when it comes test time and when it comes time to work on your homework assignments and such. So, okay, so if you spend some time on E, we know that for division, that this would be undefined, this combination would be undefined when f of x equals 0. So we know f of x cannot equal 0. So all I need to do is I need to look at the f of x graph, which is of course the one in red. I need to determine, well, where is the output equal to 0? And so if I look at the graph, I can see that f of x, this graph in red, the absolute value graph equals 0 here and also here. So these are the x-intercepts. That's when it equals 0. So at the point 0, 0 and at the point 4, 0, f of x is equal to 0. So what that means is when x equals 0 and when x equals 4, in both of those cases, we know that f of x equals 0, and then that means that g divided by f of x, would be undefined. Okay, so your answer is when x equals 0 and when x equals 4. All right, so moving on along. In our next example, we're given a function f. Now we're using capital F to denote this function, and we're going to find two non-trivial functions, f and g, such that capital F equals f composed with g. Now you may be asking, what on earth is a non-trivial function? So a non-trivial function is just one such that f of x or g of x do not equal 0. Okay, so I don't want f of x to equal 0, I don't want g of x to equal 0, but they can be any other sort of function. They could be a line, they could be a polynomial, absolute value, they could be logarithmic, exponential. What have I not covered? Basically any kind of a function that we've covered. I don't think I said square root or a radical function, rational function, anything except they can't be 0. Okay, so, and what we're doing in this situation is this capital F is going to equal f composed with g of x, okay? So this is actually what we call decomposition. So before I gave you two functions, one was f, one was g, or whatever. One was g, one was h. And I asked you to compose them. You could find f composed with g, g composed with f, G composed with H composed with F, you know, any number of things. Now we're working backwards. I'm giving you the composed function, so the function that's already been put together, and I'm asking you to find the two functions that you had to compose to come up with that composed function. Okay, so just a little bit of working backwards here. So in my first example for part A, I'm told that f of x, capital F of x, that's the composition, is equal to the square root of x plus 1. So what that means is, since capital F of x equals f composed with g of x, or f of g of x, then that is equal to the square root of x plus 1. So I want to find two functions. I want to find a function f of x. Get my pen straight here. And I want to find a function g of x, so that when I do this composition, I get the square root of x plus 1. Okay, so I need to think about what function f of x could I use, so that then when I replace the x value with some other function g of x, I'd get the square root of x plus 1. Okay, so if you think about it this way, what if f of x was x plus 1? Okay, so that's my function. What would I have to replace that x value with to come up with the square root of x plus 1? Well, of course, I'd have to replace it with the square root of x. So if f of x is x plus 1 and g of x is the square root of x plus 1, then the composition of those, so f composed with g, would equal f of g of x. Wait a minute, my parentheses are a little wonky here. F of g of x, and that would equal the square root of x plus 1, which of course is that composition. Okay, so these just take a little bit of work before you start to see the pattern. All right, so let's look at B. So for B, again, f of x is equal to 1 over x plus 3. So again, f of x equals f of g of x. So I need to determine what would f of x be and what would g of x be. Okay, so if I'm looking at this function, 1 divided by x plus 3. Well, what if f of x was 1? Let me stick with my colors here. What if f of x was 1 divided by x? What would the x need to be replaced with to get 1 divided by x plus 3? Of course, the x would need to be replaced by x plus 3. So that means g of x would equal x plus 3. And so my composition, f composed with g of x, would be 1 divided by x plus 3, because the x value would have been replaced by g of x, which was x plus 3. Okay, so take a shot at C. See if you can figure out two functions, f of x and g of x, that will give you the composed function 3 times x minus 1 cubed minus 2. Okay, so for part C, I came up with a couple of different options here, and there may be others that you could come up with. These were just the ones that came to mind for me. So if f of x was 3x cubed minus 2, and then I did the composition of f composed with g, and I replaced the x value here with x minus 1, then that would give me that composed function of 3 times x minus 1 cubed minus 2. Or you could have also done f of x was equal to 3x minus 2. So instead of 3x cubed, I did 3x minus 2. And then if I had g of x was equal to x minus 1 cubed, that would also give me that composed function of 3 times x minus 1 cubed minus 2. If you're still a little iffy on these, and sometimes this kind of tends to be one of those that once a student sees the pattern, they've sort of got it and they can go with it. But sometimes it takes a little more, it takes a few more practice, takes just a few more to kind of think through. There's definitely some additional practice in your lab manual that you'll find beneficial. And so take a look at those pages and check your work. And then typically once you work 2, 3, 4, 5 more of these, then you kind of pick up on the pattern, and then it becomes much easier to see. So now we're ready for a word problem. So we're supposed to find the number of bacteria in a refrigerated food. And then they tell us that it's given by this function, n of t, which equals 20t squared minus 80t plus 500. And this holds true, and there's a lot of t's in this. We have to keep these all straight. So where capital T is the temperature of the food in degrees Celsius. That's important. And we're told that this function only holds true, the domain of this function is for t greater than or equal to 2 but less than or equal to 14. So that's the domain of my function. Okay, if I have a T, remember capital T is temperature in Celsius. So if the temperature is less than 2 degrees Celsius or more than 14 degrees Celsius, then my function here is not going to give me an accurate result. Okay, this function only works for temperatures in Celsius greater than or equal to 2, less than or equal to 14 degrees Celsius, okay? And so this n of t value, just to keep all of this straight for us, is going to represent the number of bacteria. Let's make a note here, keep all this straight. So this represents the number of bacteria in the food based on the food temperature. Okay, and of course we know that it's in Celsius, and it only is going to be true as long as my temperature is between 2 and 14, inclusive because it's we've got those equal to signs. Okay, so we understand that formula now. It's so important. You guys are so anxious to get going and to jump in, and so what happens is you kind of generally glance through these, you grab a formula and you run with it, and half the time you don't know what you're calculating. You've calculated something, you've gotten an answer, you don't know what the answer even means. Take 30 seconds or take a minute, read through, make sure you understand, what is the formula telling me? What does T represent? What does N represent? Are there any restrictions on the domain? It's really, really important that you understand these formulas, and make yourself notes like I just did. I highlighted things that were important. I made notes because when you get into the problem and you've got a variety of formulas and you've got a variety of T's and different things going on, you're never going to remember what's what. It's much easier if you've kind of torn it apart piece by piece, made yourself some notes so that you can keep things straight in your mind. Okay, so that's only the first sentence. Second sentence is, when the food is removed from refrigeration, the temperature of the food is given by T of T, so now capital T of smaller t, and that's equal to 4T plus 2. So this is different. We need to keep this straight. So this represents the temperature of the food. Get my highlighter here. So temperature of the food is given by T of T equals 4T plus 2. And now lowercase t is time in hours. So after a certain number of hours, I can tell you what the temperature of the food is, okay? And this formula is only going to hold true when the time is greater than or equal to 0, less than or equal to 3. So greater than or equal to 0 hours, less than or equal to 3 hours. Okay, so if you've got food that's been sitting out for 4 hours, this formula, this 4T plus 2, is not going to do a good job of telling you the temperature of the food, and that's what we need it to do. Okay, so it's only, the domain is between 0 and 3. So depending on what you want to know, it tells you which formula to use. If I want to know the temperature of the food, then I'm going to use this formula. Whoops, get a highlighter here. I'm going to use this formula. That tells me temperature of the food. If I want to know the number of bacteria based on the temperature of the food, I'm going to use this formula. Okay, so depending on which one you want to know. So the formula in red that tells me number of bacteria is based on knowing the temperature of the food. Okay, the formula in blue tells me the temperature of the food based on how long it's been out of the refrigerator. Okay, well, what if I wanted to know the number of bacteria, but instead of based on temperature, I want to know the number of bacteria just based on how long it's been out of the refrigerator? Well, guess what? You can do a composition. That's this. Okay, so we're going to determine N composed with T of T, and then we're going to interpret the meaning in context. Okay, so let's come up with the composition here first. So this is N of T of T. Remember, capital T is temperature. Lowercase t is time in hours. So that's why it's so important to keep these straight. So N composed with T of T. So we're going to start with our formula for N, which was 20t squared minus 80t plus 500. But everywhere there's a capital T, I'm going to replace it with my T of T formula. So my T of T formula, I'm running out of highlighters here. Whoops. Let's see, my T of T formula, what can I use, is this one in black. So it'll be 20 times 4t plus 2 squared minus 80, capital T, again, we're going to do that replacement, which is 4t plus 2 plus 500. So all I'm doing is I'm just finding the composition of these two functions. So now I'm just going to do some algebra. So this will be 20 times 4t plus 2 squared, of course, is going to be 4t plus 2 times 4t plus 2. We're going to FOIL that. Minus 80 times 4t is negative 320t, and then negative 80 times 2 minus 160 plus 500. So 20 times 4t plus 2 times 4t plus 2. We're going to FOIL that. 16t squared plus 16t plus 4 minus 320t. Negative 160 plus 500 is positive 340. Let's go ahead and start simplifying. Now we're ready to distribute 20 to each of these terms. So this becomes 320t squared plus 320t plus 80 minus 320t plus 340. Combine all of your like terms, so 320t squared. 320t and negative 320t are going to cancel. 80 plus 340 is 420. So after all of that, this simplifies to 320t squared plus 420. Now, here's the hard part. What on earth does this represent? Well, N composed with T of T. So N, remember from up above, is the number of bacteria. So this is going to be number of bacteria but based on what? Well, my function has small t's in it, lowercase t's. Well, what did lowercase t represent? Lowercase t is time in hours. So this is the number of bacteria, t hours, after what? After the food is removed from the refrigerator. So now if I want to know how much bacteria is in that chicken that I pulled out this morning, left on the counter, and then came home after class to cook, okay, I don't have to know the temperature anymore. I don't have to stick a meat thermometer in it. I just have to know how long it's been out on the counter. And then as long as it hasn't been out more than 3 hours, because that's my domain, then I know that this function will tell me the number of bacteria that are in my chicken. That's kind of gross, really. Okay. All right, so let's move down to part B. Part B wants to know, determine the number of bacteria 2 hours. So let's mark the important stuff here. After the food is removed from the refrigerator. So 2 hours, that's within the domain. That represents lowercase t. That's time that it's been out of the refrigerator. So we're going to find n composed with t of 2. And we'll use our formula from up above. So we know that it's 320 t squared plus 420. But in place of t, I'm going to use 2. And so 2 squared is 4. 4 times 320 is 1280 plus 420. So that is 1700. 1700 what? 1700 bacteria in my chicken 2 hours after it has been removed from the refrigerator. That is your final answer. You can decide whether or not you want to eat that chicken.